You probably don't remember the Doppler effect for sound, so here it is. Apparent frequency is this weird change of the actual emitted frequency. So you got to take the speed of the observer divided by the speed of the sound wave, and then you're dividing by this 1 minus or plus, depending on the direction of the speed of the observer or the speed of the source, divided by the speed of the wave itself. And you're doing all of this to the actual emitted frequency. Wonderfully, the Doppler effect for light is not nearly so complicated. The Doppler effect for light merely says that your apparent frequency is 1 plus or minus the speed of u relative to the source. In fact, wait a second, the denominator is completely gone. What good news. Divided by the speed of the wave. And of course, the speed of the wave for light is the speed of light. And then we're going to multiply that by the emitted frequency. So first of all, this thing could get to infinity, and we can never get to infinity here. I guess you'd need to be going infinitely fast. Good luck getting faster than the speed of light, though. No, it looks like the fastest that this can get is I could get almost to the speed of light. Then I'd be adding, well, I guess I'd be adding 1 plus 1, so I could double my frequency. That's the best that I can ever do with light. I could also decrease my frequency if I'm moving away from the source, or the source is moving away from me, because it doesn't matter which one. Why doesn't it matter which one? Well, I'll tell you. It doesn't matter whether you're moving from the source or the source is moving away from you, because everyone sees light at the speed of light. This has drastic and amazingly dangerous consequences, but we're not going to go into them today. I just need you to know that if we're saying that, oh, what do I want to say? Something like, I don't know. I guess if I'm moving towards the source of the light, or the source of the light is moving towards me, either way, I'm going to get this change, and this will be a positive number. But if I'm moving away, it'll be a negative number. So here's the thing. You know that if I graph, what am I trying to say? If I make a graph of frequency of light, did you know that red is a low frequency, and green and blue and stuff, Roy, G, Biv, green and blue are higher frequencies? Did you know that? And then I'd need indigo and violet in there. This is actually a very small band, and we'll talk about that later. But this red is a lower frequency, and the green and the blue are higher frequencies. So if something is shifted towards the red, then we would say that it's been shifted to lower frequencies. What causes a shift in lower frequencies if you're moving towards the source or away from the source? You can again go back to a kid bobbing in the ocean and creating waves. If you're moving away from that kid, you're going to see the, let's try that again. If you're moving away from that kid, then you're going to see the wave frequency decrease. It's exactly the same for light. And what scientists noticed is that when we look at stars, there's always a certain signature amount of light. We'll talk about why soon also. There's so much physics coming, it's great. There's always a signature of light that comes out of different elements that are present in that star. That's awesome. And those signatures are shifted to lower frequencies depending on where we're looking to see that light. And they also know that the further away we look in the universe, the light generally gets dimmer, because of the fact that the light is spreading out, and so it gets dimmer by 1 over r squared, I guess. That's what intensity does. As you get further away from a source, you have less of a fraction of the total energy. And so I'm arguing that redshift is actually, it actually scales with getting farther away from something. So we concluded that either, as far as planet Earth, we really, really stink and the entire universe is all entirely moving away from us, or we're not unique at all. If we are not at all unique, then the entire universe is expanding. And in fact, the rate of its expansion is increasing. So the universe is expanding, and it is accelerating its expansion. What do you think the jerk of the universe is, though? Jerk, good luck.